Okay, it's 4 p.m. Indian time, and it's time for our lecture series of last Friday of a month. And this lecture is being presented by Mohamed Najar, and the topic is solid waste management by geopolymerization, the value addition, aluminium industry waste. So this will be an interesting topic, and it will be having some industrial use and of industrial value. And I would invite Mohamed Najar. He will introduce himself. He is a PhD in chemistry, as I know, and he is one of the best scientists of JNRDDC at present. And his short biography is also given in his presentation. So if you all agree, I will request our office to run his recorded presentation. It is about 35 minutes or 35 minutes presentation, and this will be followed by questions and answers. So Mr. Mohamed Najar will be on live when there will be question answer session. And till that time, please see the recorded presentation of Mohamed Najar on aluminium industry waste and its utilization. So that's going to be an interesting topic, and he is covering all the waste products of aluminium industry. So welcome, Mohamed Najar, welcome all the participants, and we will start, our office will start running the presentation. Over to Priyanka.
Areas are industrial waste processing. Good morning and welcome all of you. I am Dr. Mohamed Najar. My presentation is on the prospective utilization of geopolymerization, on the consolidation and value addition of aluminium industry rejects. This slide presents the technical background of me. I am a chemist holding PhD in applied chemistry and affiliated with Jawaharlal Nehru Aluminium Research Development and Design Center, Nagpur, India. I have 23 years of association with JNRDDC as a scientist in various domains. My major research areas are industrial waste processing and product development, geopolymer, development of rapid analytical methods for in situ and ex situ applications, hydrometallurgy, and planar chromatography. I have good number of research publications, patents, book chapters, and conference presentation in the areas of waste management and geopolymers, as well as building materials. My presentation briefly covers introduction, solid waste of aluminium industry, material properties, material input and waste generation related to primary and secondary aluminium production, source and characteristics, vision for sustainable development, geopolymer and advantages, product features and critical parameters, future scope and conclusion. Generation of rejects or byproducts is an inevitable part of industrial progress. Therefore, waste management is a matter of utmost importance in view of environmental concern and large accumulation of unused rejects. Mining, refining, and smelting are the major steps involved in the metallurgy of aluminium. Different types of byproducts are generated at every stages of the metal production and leading to the large accumulation of solid rejects having varying chemical and physical properties. Aluminium industry represents both primary and secondary aluminium production, and the overall upstream activities of metal production generates variety of solid rejects which are broadly classified into processed and unprocessed materials. In general, the rejects of aluminium industry origin are aluminosiliceous resources such as high silica and low alumina fractions. They are left unused and kept as future resources or partially used in landfills. Over the years, the outlook on process leftover or byproduct has been changed, and the leftover materials are considered as the best resource for secondary applications. Solid rejects of aluminium industry are precisely inorganic materials, and most of them are mineral-rich secondary resources. These materials are readily usable resource for industries such as building and construction, road construction, paint, pigment, and paper industries, ceramic and castables, and also useful for extracting valuable mineral values such as rare earth and precious metals. Both primary and secondary production of aluminium are left with variety of solid rejects which are useful material of productive applications. Many of the rejects from aluminium industry appears in the form of ready-usable form. The advantage of rejects from aluminium industry is that they possess innate material synergy among themselves, and many rejects materials of other sources such as steel, power, oil, biomass, etc. That means based on the chemical and mineralogical composition, these materials can be mixed together and make a composite of better quality for specific applications. The details are discussed here as alternative resource for the production of different type of building materials based on a non-fired and chemical process route. This presentation precisely highlights the potential of the processed and unprocessed solid rejects of aluminum industry origin as resources for making geopolymer products, along with technical hints of value addition for commercial exploitation. The material input and quantum of byproduct generation is very typical for primary aluminum production. The raw material input for production of 1 kg metal start with approximate 4 kgs of bauxite, and the bare process yield approximately 2 kgs of alumina. Further, the energy intensive electrolysis process additionally consumes approximately half kg materials in the form of carbon and cryolite. Since the quantum of waste generated represented the extent of pollution and material loss, there is a need for reliable and applied process options of rejects generated during the mining, processing, production as well as recycling stages. Secondary aluminum production or aluminum recycling also generate different type of waste materials. The major solid rejects generated during the aluminum recycling are filter dust, salt slag, and furnace lining. The chemical combination of these materials are good enough to make suitable combination material with other industrial rejects or rejects from primary aluminum production. Let us have a look on the processed and unprocessed rejects of primary aluminum production. Low-grade bauxite, overburdened laterite, kaolinitic condylite, partially lateritized condylite, lithomargic clay known as saprolite are some of the major unprocessed resources largely associated and available at the bauxite mining site. Processed rejects of aluminum production mainly represent red mud, aluminum dross, and spent pot lighting material known as SPL. These reject material have distinct characteristic features, chemical composition, and mineralogical composition that differentiate this material from the parent bauxite or the starting material used in the process. Kaolinitic condylite KK have similar properties of PLK and existing beneath the bauxite layer. KK possesses more silica, alumina, and less iron in the chemical composition. In India, the bauxite mines at Eastern Ghat region located at Odisha and Andhra have PLK and KK horizon. Saprolite is composed of clay minerals that results from in situ weathering of bedrock by acidic groundwater. A complete laterite bauxite profile usually comprises 4 horizons and rests on the parent rock which provides the source material for bauxitation. In most of the bauxite deposits of Western Ghat, Maharashtra, Chhattisgarh, Jharkhand, Gujarat rest on saprolite zone. Lateritic soils are formed in the tropics through weathering process that favor the formation of iron, aluminum, manganese, and titanium oxides. This consists of minerals such as kaolinite, quartz, hematite, aluminogoethite, gibbsite, bohemite, diaspore, anatite, rutile, etc. The laterite contains high iron oxide, low alumina, and high silica. The laterite derived at the bauxite mine is generally known as overburden laterite, which is removed from the top layer during the mining activities. Aluminium draws bauxite residue known as red mud, spent pot lining or SPL, filter dust, salt slag, and furnace lining are the major processed waste or reject material generated during the aluminium production. Red mud is the largest solid waste and least utilized one of all the solid rejects generated. Secondary aluminum production is mostly unorganized and have no comprehensive data about the reject generation and reuse and its utilization. Red mud is the largest and least utilized solid reject of aluminum industry. 1 ton of aluminum metal production approximately generate 3 ton of red mud. The characteristic features of red mud is high percentage of Fe2O3. Almost 50% of the total mass constitute the Fe2O3 along with good percentage of alumina and silica along with sodium and calcium. Other processed rejects of aluminum industry containing aluminosilicates are SPL, anode buds, and aluminum dross. Of late, the industrial rejects are considered secondary resources for manifold applications involving recovery of mineral values, precursor for onward processing, as well as raw materials for product development. Resource augmentation based on workable utilization of reject presents the successful model, which highlights the use of minimum processing steps, low emission, energy efficiency, speed, low cost, and marketing options, etc. The vast increase in carbon dioxide and waste generation in recent decades has been a major obstacle to sustainable development and sustainability. In construction industry, the production of ordinary Portland cement is a major greenhouse gas emitter with almost 8% of total carbon dioxide production in the world. To address this, alkali activated materials and geopolymers have more recently been introduced as a green and sustainable alternate on ordinary Portland cement with significantly lowered environmental footprints. They are used to replace Portland cement products, generally leads to vast energy savings and reduce the use of virgin materials, resulting in a sustainable concrete production. By doing so, it reuses the solid waste generated in industrial and manufacturing sectors, which is aligned with circular economy. In turn, it reduces the need for ordinary Portland cement and promotes sustainable development.
Presentation is not working. It's not audible. Kindly wait. There is some issue, technical issue, and we are resolving that issue. Kindly bear with us.
Audio is missing, I think.
Mohammad Najar, if you have a live one, please run it on this thing. Do you have a live one?
No, sir, I don't have right one right now here. So just a minute, I will check.
हाँ चलो पीपीटी चलाओ यार। अरे तुम लोग चेक नहीं किया पूरा।
Sir, you can run the PPT from there.
Yeah. We are running PPT, and
Yeah.
you can speak. We are running PPT.
No, there is the audio is there. So just run, the audio will come.
No, PPT. Let her run PPT.
Yeah.
Please move the PPT. Yes, Mohammad Najar, please go ahead. Mohammad Najar, please
Sir,
go ahead.
just a minute,
Go
sir.
ahead.
I'm connecting. Just a minute.
Please go ahead. Mohammad Najar, and she will run the PPT one after the other.
Sir, just a minute. Connecting this.
Yes.
Of late, the industrial rejects are considered secondary sources for manifold applications involving recovery of mineral values, precursor for onward processing, asset raw materials for product development, resource augmentation based on workable utilization of reject presents the successful model, which highlights the use of minimum processing steps, low emission, energy efficiency, low cost, and marketing options, etc. The vast increase in carbon dioxide and waste generation in recent decades has been a major obstacle to sustainable development and sustainability. In construction industry, the production of ordinary Portland cement is a major greenhouse gas emitter with almost 8% of total carbon dioxide production in the world. To address this, alkali activated materials and geopolymers have more recently been introduced as a green and sustainable alternate on ordinary Portland cement with significantly lower environmental footprints. Their use to replace Portland cement products generally leads to vast energy saving and reduce the use of virgin materials, resulting in a sustainable concrete production. By doing so, it reuses the solid waste generated in industrial and manufacturing sectors, which is aligned with circular economy. In turn, it reduces the need for ordinary Portland cement and its consumption and subsequent emission of carbon dioxide to the environment. As displayed in the previous slides, the chemical composition of almost aluminum industry.
Yeah, next. Mohamed Najar, please speak.
Yes, sir, it's coming, just coming.
Speak. No need of waiting for recorded presentation.
Okay, yeah. So aluminum industry rejects possess high mineral values and excellent properties suitable for making sustainable building materials useful for infrastructural and construction applications. Sustainable construction refers to the adoption of building designs, construction method, and materials that are environmentally amenable. Through sustainable construction, we optimize the use of natural resources via recycling and reuse of materials so as to reduce our dependence on natural raw materials.
Industry rejects possess high mineral.
Mohamed Najar, please take over.
Process is one of the most effective and environment-friendly process route for converting different type of industrial rejects into useful materials, especially into building units. The geopolymer process or geopolymerization is required no heating or firing. The process can take place at ambient temperature and no emission is taking place during the process of geopolymerization and the binding is taking place without the use of cement. Synthesis or production of geopolymer involves three process steps: mixing, molding. JNR conducted thorough studies on synergistic utilization of about 75 industries and combination for making geopolymer products for building and construction. Lightweight, form type, sandwich type, and hard and high strength products were developed by the non-fire group for suitable commercial exploitation. The studies identified good synergy among aluminum industrial rejects, steel industrial rejects, as well as biomass-based rejects such as rice husk ash, bagasse ash, and corn cob ash, etc., for development of green building material based on geopolymerization. The three simple steps of mixing, molding, and curing makes the geopolymer matrix. Mixing for alkali activation of raw material is most crucial since all alkali activating materials are not make the geopolymer product. To make geopolymer matrix, low pressure aluminum silicates are generally preferred. The reject materials such as PLK, KK, laterite, etc. are best suited for making geopolymer matrix. The structural units of geopolymer is different from three-dimensional structure, while the alkali actuated metrics have no three-dimensional structure. They mostly exist in U3 structure. So even if alkali actuated materials have higher strength than geopolymer, they have very fewer durability properties than geopolymer. Alkali actuated materials are not polymers, so they cannot be called geopolymers. And many scientists and civil engineers are mistaken alkali.
Dr. Najar, please speak.
As building material. The use of mixed raw material facilitate the availability of alumina and silica for faster reaction in alkaline medium. For example, red mud is mixed with fly ash and rice husk ash, and the geopolymer metrics have shown about 19 megapascal of crushing strength. The input of fly ash is not suffice the easy availability of silica in view of the presence of quartz instead of amorphous silica. The requirement of amorphous silica for alkali actuation reaction is achieved by the input of rice husk ash. Similarly, the required crushing strength for a specific combination matrix can be achieved by the selection of suitable material combination or by changing the ratio of material input, or we can change the concentration of sodium hydroxide and sodium silicate in the actuator medium. So the flexibility of choosing the concentration of alkali actuator and the mixed design as a whole makes this technique more preferable for making geopolymer matrix for building and construction application, or the same matrix can be used for making low strength material for low load bearing application such as decoration purpose, wall tiles, or partition walls, etc. When we make geopolymer for construction and building applications, the following parameters are decisive and related to the material properties. Crushing or compressive strength of geopolymer is directly proportional to alkali actuator concentration and curing temperature. Water absorption depends on the curing temperature and dry mix composition. That the physical synergy of material have a direct impact on water absorption. Increasing polarity and decreasing curing temperature, efflorescence of geopolymer increases. Density of geopolymer not depend on the concentration of actuator. It mostly depends on the nature of raw material composition.
Slide number 24.
Increasing building construction is one of the fastest growing drivers of carbon emissions. Therefore, energy conservation and carbon reduction in building have become increasingly crucial in the context of global carbon neutrality. Construction is the second largest industry in this world. Embodied energy, carbon emission, economy, utility, durability, and comfort are the main concerns of current classical building design. In order to reduce the carbon footprint of infrastructure, it is important to account the energy that is embodied in the material that we use. Embodied energy is a sum of energy requirements associated directly or indirectly with the delivery of goods or services. Energy used to extract, manufacture, and transport all the materials to be used. For the overall analysis of developed geopolymer, it is observed that with the increase in the sodium hydroxide molarity, the compressive strength, embodied energy, and carbon dioxide emission increases. A comparative study on the variation of embodied energy and carbon dioxide emission with respect to the increasing concentration of sodium hydroxide in alkali activated medium is shown here. The dry mix design used was a mixture of fly ash and laterite in 1:1 weight-weight ratio. It was observed that the XRD data or mineralogy of material is useful for choosing the right combination of raw materials based on the presence of active mineral phase within the component oxide. For example, the provenance of crystalline quartz and amorphous silica in total silica, as well as more active gibbsite, less active bohemite, and least active diaspore in minerals usually present in low-grade bauxite, overburden laterite, and other clay mineral rejects at different ratios in total alumina for alkali activation at ambient condition. This information of active mineralogical phases within the specific mineral oxide is also useful for measured use of alkali activator, that is a combination of sodium silicate and sodium hydroxide for geopolymerization. The reserved use of alkali activator in geopolymer facilitate better economics and quality of geopolymer product. Proper use of alkali for activation of active mineral phases in the raw material marks low efflorescence and material strength by encapsulating the less or non-active mineral phases or mineral components within the geopolymer three-dimensional structures based on the tetrahedron sharing of active aluminum and silicon atoms. Further, the limited or controlled use of sodium hydroxide and alkali activator keeps a cap on the emission of carbon dioxide as well as embodied energy in the overall geopolymer matrix. A comparative study is presented to affirm the superior quality of geopolymer-based building material. Physical properties of overburden laterite-based geopolymer brick was compared with the commercially available burnt clay and fly ash bricks. The comparison showed that the density of OBL brick is 12.5% and 12.2% lower compared to burnt clay and fly ash bricks respectively. The achieved compressive strength of OBL at ambient temperature is far more than that of burnt clay and fly ash bricks, which will ultimately help in saving energy required in case of heat curing. Overall, the developed geopolymer brick using laterite as primary raw material resulted in performance improvement. Wherever higher strength of brick is a criteria, these geopolymer bricks can be conveniently used for construction purpose. The following are the inference of the case study. Compressive strength of OBL geopolymer brick is as high as 23 MPa. The water absorption and efflorescence are well within the permissible limit given by Indian standards. Compared to burnt clay and fly ash brick, the basic properties of geopolymer blocks developed shows that it can be used in building and construction as a substitute for burnt clay bricks or clay products, depending on the purpose and engineering models. Apart from that, the described process, geopolymerization, can contribute significantly to the environmental preservation, since there is a practical possibility of converting large quantity of aluminum silicious industrial rejects as alternate building materials. This This mineral-rich resource need to be exploited with respect to the chemical and mineralogical parameters for developing value-added products at ambient conditions, thus saving energy, environment, and natural mineral resource for future needs. The scope and application of geopolymer are not just limited to building material. Toxic immobilization by geopolymerization, 3D printing related to building and construction, preparation of geopolymer ceramics are some of the latest attractions of geopolymerization. Coming to the conclusion, geopolymerization is useful for making wide range of building materials without firing and emission of greenhouse gases. Building and construction industry possesses the space for consuming largest volume of industrial rejects and geopolymerized building materials. Solid rejects of aluminum industry origin are best suits for making wide variety of building materials with or without the addition of materials from other sources. Chemical and mineralogical data of raw materials need to be considered for making mixed designs of geopolymer products for reduced use of commercial ingredients as alkali activator. Since the embodied energy and overall carbon dioxide emission is directly proportional to the alkali activator composition, calculated use of sodium hydroxide is advised for making activator composition. Scope and use of geopolymer as a reliable medium for containing heavy metal pollutants, radioactive elements, and other toxic components for safe disposal need to be investigated.
Here we are presenting some of the latest publication from JNRDC related to geopolymer and industrial aluminum industry waste utilization. This is one of the small video that is showing how lightweight formed geopolymer can be prepared from red mud and fly ash mix.
Thank you.
Yeah, thank you, sir.
Thank you, Mohamed Najar. Sorry for the inconvenience caused because of some technical fault, and we are very sorry for this interruptions.
So the video is available on YouTube. So in case
video, yeah, is available on YouTube. So, and also we will upload whole presentation on IBAAS website. So please have a look. And now the session is open for discussion, and please ask question to Mohamed Najar. I also have some question which I will ask later on. Okay. So please start with audience. Please ask questions to Najar, Mohamed Najar. That will clarify the whole geopolymerization process. Please, you are welcome. So I think people will come one by one for the questions. My first question is, the red mud or bauxite residue already contains some caustic soda.
Yes.
Do you need extra caustic soda for this, or can you use the same caustic soda for geopolymerization?
Sir, the soda available with red mud is totally free, not free for making geopolymerization. The free soda, whatever is available in the red mud, is useful for making geopolymer. So that is one of the advantage when we use red mud as one of the raw material for making geopolymer.
So you need not add any more caustic soda in that one.
No, not like that. So it is some percentage of soda is available. So that we have to add more alkali for alkali activation.
So you have to add some fresh NaOH or caustic soda in the system.
We call it a alkali activator solution. It's a mixture of sodium hydroxide and sodium silicate. So red itself is having very less quantity of silica. So preferably we add some siliceous materials along with red mud to compensate that lower range of silica in red mud.
So even fly ash is added. That doesn't, or you can add some silica-rich clay and other material also there, no?
Exactly. The problem with the fly ash is that most of the silica available in fly ash is in quartz form, not in. So we actually need free silica for making geopolymers. So materials like PLK, KK, or even biomass origin ash such as corn cob ash, all these materials, rice husk ash, all these are very much used for making geopolymer.
So clay can be added?
Yeah, clay can be added. If clay is
please do not use PLK, KK. People, they don't understand many of the PLK partially lateralized chondrolite. This is only for Eastern Ghats.
Exactly.
Fulminized chondrolite. So just tell clay and whatever is available below bauxite zone. It's mostly clay material.
Yes. Even low grade are also useful.
Yeah, so PLK, KK is very specific to the Orissa and Andhra Pradesh bauxite. Whereas in the world, many places clay is occurring. So better to say clay can be added.
Clay minerals are very well utilized.
Okay, please open for questions, please. George, Venebulgi.
Thank you for calling me. Well, I'd like to ask which are the materials which can be replaced with these geopolymers, and how are the comparison of the costs of the traditional materials. And maybe the last question of me, that whether you have reached the stage of the industrial application, or is it a pilot scale application? So this is a very interesting field of development, but I'm asking the context of this. Thank you.
Okay, thank you. So actually, geopolymer materials, when we use for building materials, it is intended that the geopolymer probably going to replace cementitious material, or the consumption of cement can be reduced by use of geopolymer based building material. This is one of the highlighted area about application of geopolymer. So the properties of cement and geopolymer, when we compare with time, the crushing strength or the physical properties of cement deteriorates. But when we compare the quality of geopolymer material with time, the crushing strength and the physical properties of the hardness, etc., keep on increasing. Moreover, geopolymers are acid resistant, alkali resistant, and they are very well withstand the weathering conditions. Compared to that is the advantage when we are comparing cement and geopolymer based building material. So in addition, geopolymers having other applications, not only limited to building application, other application. So for example, if there is a red mud that is having radioactive elements, or for example, red mud or bauxite from Australian region, so there is a apprehension that there is a lot of radioactive elements are there. So if we wanted to dispose these radioactive elements along with red mud, the open space is not probably advisable. So if we can geopolymerize these materials and deeply buried in soil or water, that is another advantage where geopolymerization can be applied. That is waste disposal, safe disposal of waste material.
And So what about the industrial application, or how is what is the stage of the development?
Yeah. So our work is closely, we have close interaction with some of the local industries. They are part of this project activities what we have executed at JNRDC. Partly they funded the project activities along with Ministry of Mines, Government of India. So they have a plan to set up a pilot plant followed by a production unit in one of the nearby districts of Nagpur in India. So probably they are going to use steel industry rejects and aluminum industry rejects in certain specific ratios.
Thank you, sir.
Thank you. Thank you.
So what is that aluminum industry reject? Is it bauxite residue?
It is bauxite residue and fly ash both, because the captive power plant is also generating a lot of fly ash that is also available with aluminum industry.
And what is steel plant rejects?
It is mostly granulated blast furnace slag and bottom ash. These two materials are very well useful for making combination material with the aluminum industry rejects, that is red mud or even fly ash.
Okay.
Thank you, sir.
Any more question? Takuo, please.
Thank you. One question. Thank you very much. Very interesting presentation. It was a little bit difficult for me to understand, but my question is, how about the reaction rate? Is the reaction or consolidation progress very rapidly compared to cement or other materials? I guess it's a little bit slow reactions. How about it?
So cement is ready available binder material. So the only thing we have to just add water and make a paste and use for binding purpose. In geopolymer, so it is a chemical reaction. So it is nowadays there is a idea that we have to keep the ready mix available and mix with alkali. So practically there is no such applications are going on in India right now. So we are, whatever geopolymer research what we have done in India is based on slurry based material. So the chemical reaction is fast when we use strong alkali. So that is obvious. The problem with using strong alkali is that there is a side reaction and there is a chance of efflorescence. So better we go with the mineralogy and chemical composition of material, then accordingly we use the alkali reagent. So maybe it is a slow reaction, but it's a permanent reaction.
How much you can replace cement in the industry if it goes successful by geopolymer?
If it is a successful process, we can replace 100% cement, because cement is not required for geopolymer binding. It is a complete binding based on geopolymerization. Zero cement is utilized when we go for geopolymer based products.
So is there anywhere in the world they are using geopolymerization material in place of cement?
So it is probably it is in use in US and European countries for making runways and buildings, that is available in Google, and so not in commercial basis. That what I came. That's my knowledge right now. So probably they are also planning to go in commercial basis for making runways and building materials in European countries.
Okay, interesting.
Thank you.
Thank you. Please ask question. Please, anybody from audience, you are welcome.
Hello.
Hi, sir. Abhishek here. I just want to know what's the cost ratio when you replace with the cement?
So the major cost involved in the preparation of geopolymer is the commercial ingredients, that is sodium hydroxide or any alkali that we are using for alkali activation. Maybe it is sodium hydroxide and along with sodium silicate. So if we have a choice of getting waste material as alkali origin or usable as an alkali in place of commercially available sodium hydroxide or sodium silicate, so well and good, we can reduce the cost. Then the advantage of making geopolymer is that almost all inorganic industrial waste can be converted into geopolymer. So this cost is depend on other factors such as transportation cost, then labor cost, etc.
Thank you, sir.
Welcome.
Anybody else? Anybody else? Sharad Kumar or anybody is Pallavi Deshmukh? Anybody can ask question? Okay. The presentation is available on will be available on IBAAS website, and there will be a contact details of Dr. Mohamed Najar. If anybody wants to discuss in detail, he is welcome. He can contact Mohamed Najar and find out the detail of this process. And thank you very much for your participation. Although there was some hindrances, there were some technical flaws, but ultimately it has gone well. And the next presentation will be by Alex Saboyage. He is ex-BHP Bulletin. He will be talking on some aspect of the alumina technology. We will shortly announce his presentation. Thank you very much. Goodbye.
Thank you very much,
everybody.
Goodbye.
Thank you, sir.
Thank you.
Goodbye.
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 Thank you, sir.
Bye, everyone.
Thank you.
Thanks.
Thank you, sir.
Thank you.